Hi, my name is David Jensen,
And I'm Krish Patel.
and today we're going to be talking about our 4800 electronic instrumentation sensor board project. So for our project, we chose to do an angle sensor, which will allow users to set a desired X and Y angle. And once that angle is reached, it will give an auditory and visual cue through the buzzer and light that you're at your desired angle. The inspiration for this project was actually a lab, the ENEE 1030 lab, where one of the one of the lab experiments had us setting a projectile platform to a specified angle that was very precise. And it was challenging to try to get the angle set properly by yourself while looking at the angle gauge and tightening things down, making sure that it's not changing. It was just there was a lot to try to keep straight there. So in this with this project, you would be able to get a auditory and visual cue. The buzzer would be sounding, the light would be green, so that you can focus solely on tightening down the platform, setting it at its angle, and you know without looking that it's at the proper angle. So expanding on that, we did some brainstorming and thought of ways you could introduce this into manufacturing or safety systems. So in a manufacturing environment, you could integrate this system into a larger control system for, say, welding, a robotic welder. If you needed to have a object positioned at a certain orientation before the welding took place, you could set your angles in this, and whenever that angle is reached, it would send an output to start the welder. A simple flip of logic would also allow this to be used as a safety system for various applications where a object or platform needs to remain in a certain range. So you could do that by setting the desired angle that it needs to stay at and flipping the buzzer logic so that while it's in that range, there's no buzzer and the light is green. And then whenever it exceeds that threshold, the light would turn red, buzzer would sound, and you would get a very obvious indication that you're out of the safe range there. So I will be walking through the coding and logic portion of this, and Chris will be giving the physical demonstration of our board. So we'll jump over here to LabView, and I will show the front panel first. So this is our front panel. It's sectioned off into three sections here. The user controls on the left. And so these controls down here allow you to set your desired angle input. And then you have your stop button, which just stops execution of the program. And status will let you know that the program is running properly or if there's any errors or anything there. Sensor readings, you have your raw sensor output in volts, and then you have your corrected version as a percentage of G. That's for the X and the Y there. On the right, we have the status, and so we have a target achieved light and a buzzer light. So when the desired angle is reached, this red LED will turn green, and the buzzer will also light up green, letting you know that you're in your proper range. So we're going to move over to the block diagram. The majority of this is copied and pasted from one of the example files that were provided. And then we did our own, we added in our own logic and reworked as needed to make the system work properly. So the larger structure here is a flat sequence structure that's sectioned off into three pieces. The leftmost is the initializing section. The middle is the main loop, and the right is the closing. So the left and right sections are direct copy and paste. And then the middle is where we made all of our changes here. So just following this line, this initialized data here, it feeds in, and we also have a while loop here. Forgot to mention that. That's nested inside the middle sequence. So the initialized data feeds into our analog input ExpressVI, and and it feeds this error out signal to our stop conditions. So the loop will stop when either the stop button is pressed or an error is detected. And then that feeds out to this reset VI and this error out block that are both responsible for resetting and displaying errors. And then this analog input express VI is where we configured our sensors. So we removed the Z accelerometer because it's not needed for this project. And then we ensured that the proper pins were being used for our MyRio board. And that allowed us to take the sensor measurements and use them in our code here. So we're feeding the raw X and Y readings into these two blocks here, which again, these are mostly copy and paste. We made some adjustments to zero them out properly. But this is just correcting the raw voltage input to a corrected version that's a percentage of G that's more intuitive and easier to understand. So we then take that corrected measurement and we sent that into our target logic blocks, which these allow the user to set their desired degree input, and it will compare the measured value against that value and determine if you're in the range that you want to be in. So this control block here is where you set your degree. It's on the front panel. And then we multiply that with this scalar that maps the degrees to the raw or the percent G measurements that we're getting directly from these sensors. We then take that and add and subtract an error to get a plus or minus 0.03 for a tolerance. And then we compare that value against our measured value to make sure that our value is less than the upper threshold and greater than the lower threshold. Once both of those conditions are met, that means we're in the range that we want to be in. It will satisfy this AND block here and feed a true Boolean through to this AND block down here. The Y target is the exact same flow. So once those conditions are satisfied, it will send a true, and then this AND block will be satisfied. That will then feed out a true Boolean along these branches here. So the upper one here is our buzzer logic, which is pretty simple, pretty straightforward. We're taking a Boolean input and a selector. So while this Boolean is false, which is just the idle state, we'll be feeding a 0 through the selector, and it'll give us a duty cycle of 0, meaning our buzzer is off. Whenever this evaluates true, we will select the 0.25, and our duty cycle will be 0.25, our buzzer will come on. Frequency is just set to a constant 2500 hertz. Moving down to the next section here, we have our indicator logic, which is the indicators that are displayed on the front panel. And this will be useful, especially in a manufacturing or safety environment where the control panel may not necessarily be directly next to the lights and the buzzers, or you might want to have remote indicators somewhere else. You could hook them up here, and this would, again, allow remote indication of the system status. Moving down to this final block here, this is our light logic. And so when this is in idle state, this Boolean is false. It will feed down into these two select blocks for our red LED and our green LED, which they're controlled by the duty cycle of the PWM. So it's one LED, RGB LED that's controlled by the duty ratio. So when this is false, this not block flips it true, and this 255 is selected. That's divided by 255 and gives us a duty cycle of 1. So our red LED is on full intensity. Whenever this Boolean is evaluated true, this flips to false, a 0 is fed through, red LED goes off, and then the opposite happens for the green. So 255 is fed through, divided by the same, and you end up with a duty cycle of 1, green LEDs on. This entire loop is timed by this timer block here, which allows it to repeat every 200 milliseconds. And this just slows down program execution and lets you get a little more stable readings. With that being said, I think that covers our logic flow and code.